Let's look at a reaction between a molecule called butadiene. Now it's called but because there are 1, 2, 3, 4 carbons, and it's a diene because there are 2 double bonds. Between that and a molecule called hydrogen bromide, which has a formula HBr. Let's say we run this reaction once at 0 degrees Celsius. What we would get is actually 2 products, not just 1 product. So the first product has the double bond between carbons 1 and 2 and the bromine at carbon 3. Let's say we get 80% of this product. And then we also get a second product, which is similar in structure but slightly different. And this time the double bond is between carbons 2 and 3, and the bromine is at carbon 1. And so if we get 80% of this product, we get 20% of the second product. And then let's say we run this reaction again, so the same starting molecules. We have butadiene and good old hydrogen bromide, except the difference is this time we run the reaction at 100 degrees Celsius, so it's fairly warmer than the previous reaction. And this time we get the same 2 products, except we get them in different ratios. This time, let's say we get only 15% of this first product, and we get 85% of the second product. So in order to sort of delve into why this happens, let's study the reaction mechanisms. We start with our reactant, which again is butadiene, and now let's look down here at this reaction coordinate diagram I've drawn. So what this will show us is sort of how the reaction is progressing. That's reaction coordinate, and it compares that to the energy. So as we go up, we increase in energy. However, increasing energy means we actually decrease in stability. So the higher up we are on this, we have more energy and less stability. So let's call this our reactant R, and let's say our reactant has an energy that is right here. So that's R. And again, we're reacting this with hydrogen bromide, which is HBr. And so what happens is the pair of electrons from one of these 2 double bonds, it doesn't matter which double bond because this is a symmetrical molecule. So these are essentially the same. So let's say this pair of electrons from the double bond attacks the hydrogen, and that's going to cause the bond between the hydrogen and bromine to break, and the pair of electrons jump onto bromine. And so what this brings us to is our first reaction intermediate. So the first intermediate has the double bond between carbons 1 and 2. The hydrogen is attached at carbon 4. Now I'm not going to keep drawing in this hydrogen because it's sort of implied with the skeletal model. And then we also have what we call a carbocation. So that's a positive charge at one of the carbons. Cation is a positive charge, carbo is carbon. So this is not just a carbocation, it is a secondary allylic carbocation. And so what that means is, again, it's a carbocation because there's a positive charge on a carbon. It's secondary because there are 2 non-hydrogen species attached to the carbocation, and then the carbon with the carbocation, and then it's allylic because it is 1 carbon away from a double bond. So we have a secondary allylic carbocation, and let's call this intermediate 1, or I1. So let's say intermediate 1 has an energy that is right about here. So that's I1. And we can't forget about our bromide ion, because now it has a negative charge. And so what happens is this negatively charged bromide ion, the electrons there attack the positively charged carbocation, and we get our first product, which again has the double bond between carbons 1 and 2, and it has the bromine on carbon 3. And let's call this P1 for product 1. And let's say P1 has an energy that is here. Again, I've omitted the hydrogen here because we don't really need to draw it anymore. I just wanted to show where it goes initially. So this is how we get our first product. Now how do we get the second product? Because we see down here that there are 2 products formed. So what happens is this secondary allylic carbocation actually has a resonance form. And remember, resonance forms are not real structures. What the intermediate actually looks like is some hybrid between these 2. So I'm going to redraw I1, which is our first intermediate. And again, remember that I am not drawing the hydrogen. That was where the pair of electrons from this double bond jumps to the middle position, and then this is our second intermediate. This is our second intermediate. Again, it has the double bond now between carbons 2 and 3, and it has the carbocation. Let's look at a reaction between a molecule called butadiene. Now it's called but because there are 1, 2, 3, 4 carbons, and it's a diene because there are 2 double bonds. The reaction between that and hydrogen bromide, which has the chemical formula primary allylic carbocation. And it's, again, carbocation means there's a positive charge on a carbon. Primary this time means that it's only the primary means that there's only one non-hydrogen species attached to the carbon with the carbocation, and then allylic means that it is one carbon away from a double bond. And so let's label this as I2 for intermediate 2, and let's say intermediate 2 has an energy that is all the way up here. So we notice that I2 is higher energy than I1, and both of them are higher energy than our reactant, R. And then the reason we might get this primary allylic carbocation, that is I2, is because it has a double bond that is more substituted than I1. And more substitution on a double bond means that it is more stable. And again, substitution means that there are things attached to the carbon. So there are 2 things attached to the double bond in I2, and only 1 thing attached to the double bond in I1. That said, the primary part of the carbocation still does make this I2 more unstable or higher energy than I1, but the double bond does prefer being more stabilized. And just as a point of reference, this is not just a primary carbocation, this is a primary allylic carbocation. And the fact that it is 1 carbon away from the electron-dense carbon bond stabilizes the positive charge that is the primary carbocation. If there were no double bond here, then this would really not exist. We don't have primary carbocations in nature, but we do have primary allylic carbocations. And so let's continue with the reaction. So again, we have our bromide ion and the pair of electrons that give it that negative charge attack the positively charged carbocation, and we get our second product, which again has the double bond between carbons 2 and 3, and then the bromine at carbon 1. And so I'm going to label this as P2 for product 2. And product 2 has an energy that is all the way down here, let's say. So now we have sort of the mechanism for how we got to our 2 products through 2 intermediates from the same starting materials. And the reason that we get these 2 products, if we look down here again at our 2 different reaction conditions, one was at a lower temperature, one's at a hotter temperature, is an idea called reaction control. And so reaction control falls into 2 categories. We have kinetic control over reaction, and notice that this is in this sort of, what does the computer say, honeydew? This is honeydew colored, and so are P1 and I1, same with down here. And then the other type of reaction control is thermodynamic. And you'll notice that in this sort of lavender color, I've labeled I2, P2, thermodynamic, and same down here on our reaction coordinate diagram. Before I proceed further with this explanation, let me fill in, or continue filling in, our reaction coordinate diagram, because we don't just like lines, we like smooth curves. So to get to our first product, we have our reactant, and the reactant goes up to a transition state, and down to I1, up to another transition state, and down to P1. And then let's sort of follow the same roller coaster, if you may, for a visual example or for visual reference, to get to P2. Remember, this is how we get to P2. So we start with our reactant, go up to the same transition state, go down to I1, which is the same for both, go up to another transition state, and down to I2, and then we continue up to a third transition state, and all the way down to P2. And again, P2 is lower energy than P1, I2 is higher energy than I1. And so let's sort of explore the differences between kinetic and thermodynamic reaction control. So if we look back down at the two different sets of reaction conditions with the same molecules that yielded the two different products, we notice that one is at a low temperature and the other is at a higher temperature. And we get more of product 1, which is our kinetic product, formed at the lower temperature, and more of product 2, which is our thermodynamic product, formed at the higher temperature. So what we can say about this is that kinetic control happens more at lower temperatures. And on the same token, thermodynamic control happens at higher temperatures. And we'll see the reason for this in just a second, actually. But first, let's notice that in our reaction coordinate diagram, the reaction coordinate can also sort of be a time axis. I wouldn't say it's exactly a time axis, but if we were to sort of imagine it as a time axis, we start with our reactant, and the first thing that forms is intermediate 1. So I1 is always formed first. And then if we continue thinking about this as a time axis, it'll take more time for I2 to form. And also on the subject of the intermediates, I said before that I1 is higher energy or less stable than the reactant R, and I2 is also higher energy and less stable than our reactant R. But if we compare the two intermediates, which I did before, we also notice that I2 is higher energy and less stable than I1. So intermediate 1 is more stable. And on the same token, intermediate 2 is less stable. And just to sort of correlate this with energy, so more stable means less energy, and then less stable means more energy or higher energy. Now, I've actually left a few things out of our reaction coordinate diagram, so let me put those in. So to get up to our three transition states, our four transition states, I guess I should say, this involves some energy. Notice how we start from R, and to get up to I1, we actually go higher up to our transition state. So that is a special kind of energy called activation energy. So we might call that E sub A or delta G double cross. And I'm going to call it delta G double cross 1 here. And then to get to product 1, we go through delta G double cross 2. And then to get to our second product, we go through a different set of these activation energies, or delta G double crosses. We do go through delta G double cross 1, but then we go up higher to, let's call this delta G double cross 3. And then we have delta G double cross 4. And so looking at all of these and keeping in mind that these are the activation energies to get from either reactants or intermediates to the transition states, we can see that the kinetic product, or the kinetic reaction control, involves less activation energy. It only has delta G double cross 1 and delta G double cross 2. So if we sort of think of it as the sum of those, again, the kinetic reaction control or kinetic product requires less activation energy, which I'm abbreviating E sub A. And we can sort of think about that mathematically as delta G double cross 1 plus delta G double cross 2. And on the same sort of token, we notice that it takes not just delta G double cross 1, but also delta G double cross 3 and 4 to form product 2. So we can say that product 2 requires more activation energy. And again, this is delta G double cross 1 plus delta G double cross 3 plus delta G double cross 4. So there's more activation energy, or E sub A, required to get to our thermodynamic intermediates, and thus to our thermodynamic transition states, and thus our thermodynamic product. So less activation energy and more activation energy. And if we look back up to the temperature conditions that sort of yield these products, we see that the kinetic product, we have more of that at a lower at a lower temperature. And temperature is a measure of the energy, and if we need less energy for the kinetic product, then it'll happen more at a lower temperature. Whereas to form the thermodynamic product, we need more activation energy. So a higher temperature will sort of provide that greater activation energy that we need to get all the way up to these transition states and down to product 2. And then another thing to note, let's go back to our reaction coordinate diagram. We not only have the difference in energy between the intermediates and reactants in the transition states, but we also have the difference in energy between the reactants and the products. So we call this delta G, and I'm going to call it delta G1 for P1, and delta G1 is the Gibbs free energy, or sort of the energy that's released in going from the reactants to the product. So not only do we have that, but we also have a Gibbs free energy, or a change in energy for our second product, and so let's call that delta G2. And notice that delta G1 is less than delta G2. Another way I could sort of compare these two is that P1 is higher energy than P2. And so what that means is that P1 is actually less stable. And on the same token, because P2 is lower energy, that means P2 is more stable. And another way we can think about these, again, is that P1 is at a higher energy, and then P2 is at a lower energy. And so kinetic versus thermodynamic reaction control, this is how we get two different products from the same starting materials. And again, if you run this reaction at 0 degrees, we get this sort of ratio where we have more kinetic product than thermodynamic product, lower temperature, more kinetic product. And then if we run it again at a higher temperature, 100 degrees Celsius, we get more of the thermodynamic product. So higher temperature, thermodynamic product. And then one final note on why P2 is more stable than P1. If you look at P2, just like for its intermediate, P2 has a more substituted double bond, and that again means there are more things coming off of the double bond that are not hydrogen than P1, and a more substituted double bond is more stable. So that is another reason why P2 has less energy and is more stable than P1, which has more energy and is less stable.